All right, so last time we developed a weak form and then we put it in this bilinear form where we had terms that involved del u and u and terms that only involved del u. And we called this the variational problem. And then also we use that to infer a quadratic functional that looked like this. And I said that solving the variational problem, solving the first equation, is equivalent to minimizing the quadratic functional I, right? And when we actually, so strictly when we use an approach that minimizes the quadratic functional, what we're doing is strictly called Ritz method, and then we're going to work an example today, okay? And then I mentioned that the finite element method is just a piecewise extension or a piecewise implementation of the Ritz method. But in the finite element method, we don't really minimize the quadratic functional. We rather solve the first equation, okay? But I want to give you an example of just using Ritz method one time so that you can kind of see where the mathematical roots of the finite element method come from. And there's some history here that sort of makes this significant because when the finite element method was first invented in the late 60s, it was very, very dismissed by the mechanics community at large or the mathematics community because, again, it was sort of introduced as this matrix method in structural mechanics, and that then when you extend it to, say, finite elements over continua, it wasn't well accepted, and it was very, very much dismissed. But then once the mathematicians sort of got a hold of it and realized that it's just a piecewise implementation of the Ritz method, which has been well accepted and established for more than 100 years, then it sort of led to some acceptance of the method, which, of course, now, I mean, it's sort of hard to believe that the finite element method ever was met with any kind of dismay because it's sort of the way we do engineering at this point. Right? I mean, it's ubiquitous. Okay. So in the Ritz method, we're going to use the weak form, or more specifically, the quadratic functional we infer from the weak form. And this has the advantage that the approximating functions those are the the interpolants. I think maybe last time I used phi. They only need to satisfy the essential boundary conditions since the natural boundary conditions are included, right? They're already in the weak form. So we seek an approximate solution, UH, that's of the form and that's probably the sixth time I've written that, right? So the CJs are unknown coefficients, and the phi j, or the phi j's are interpolating functions of x in 1D. And what we do is when we plug in this approximated function into our quadratic functional, right? So when we plug in u of h into the quadratic functional, our functional becomes a function, right? So remember that b and l, well, they have integrals in them, right? So it's a function of functions. But then once I plug in this approximation, I can then compute those integrals, right? These are just unknown constants. So I can just pull those out and compute the integrals then, okay? And now I just have a function of unknown constants, right? After I compute the integrals, I just have a function of unknown constants. And once I have that, then I can just use the method. So, you know, substitute in u of h, integrate. Now I have just a function of x, right? And c, right? I'm sorry, not even a function of x. Then I just have a function of the unknown constants. And then I can just use the methods from ordinary calculus to determine where there's a minimum, right? So then I just take the partial derivative with respect to each Cj, set that equal to 0, and that gives me J equations that I can then solve for the unknown C's.